Bismillahirrahmanirrahim. Assalamu alaikum. So in this discussion we will discuss, we will be stepping towards defining the so-called complex integration. But before we start this complex integration, we will revisit, or we will state some of the terminologies, notions related to the curves, or you can say that curves in the complex plane, or you can simply say that complex curves. So curves in complex plane. So let's talk about this. So if we have a curve in complex plane, let me draw this over here. So suppose we have got this complex plane where this x-axis is the real axis and this is the imaginary axis, right? Let me say that I have this curve which is located in this complex plane now. So each point on this curve z can be defined by a complex function z of t to be x of t plus iota times y of t, where t is running between two real variables a and b, so two real numbers basically, a and b. Now this z, which is x of t plus iota times y of t, is a function. So this function, which is a complex valued function, defines parametrization of my complex curve. Parametrization of the curve C. So C means this curve, right? Okay. So far what we know is, if we have got a complex curve, then we would like to have, or we would try to have, its parametrization. One example for this so-called parametrization is going to be the parametrization of circle, where we set x of t to be cos t and y of t to be sin t. So in that case, when I will make this function z of t, which is cos of t plus iota times sine of t. Now this function right over here is defining such that t is running between, let's say, 0 and 2 pi. Now by this function z is basically defining the parametrization of circle in the complex plane. Parametrization of circle in complex plane. We can talk much more about the curves, but I will be, short. I'll be talking shortly, and I'll try to come up with the detailed sessions in this series on the complex curves as well. So far so good. So far we have this if we have a curve, complex curve, then we have its then we can have its parametrization, and once we so we have an example of the parametrization of a complex curve that we have stated over here. Furthermore, suppose we have a curve C now. As you know that if we have got a parametrization of this C, then it is given by x of t plus iota times y of t, where t runs between a and b. So z of a, when we compute, is going to be x of a plus iota times y of a. This point z of a is called the initial point of the curve. Initial point of the curve, right? So this point, let's say over here, is z of a, and then the point z of b, which is basically x of b plus iota times y of b, is the terminal point of the curve. Terminal point of the curve, right? So this point, let's say over here, is z of b. So our curve A has the initial point given by z of a and its terminal point given by z of b. Let's define smooth curve. Smooth curve. let C be a curve in the complex plane, parameterized by the function z of t given by x of t plus iota times y of t. Then C is said to be smooth. So this curve is said to be smooth if what happens, if number one, z has continuous derivative. So this derivative of this z is continuous for t in the interval where t is running. So for this parameterization, t is running, let's say, between a and b. So for the interval I, which is given by a to b. So this, I think this has to be open interval, right? So like you can say that this, or maybe it is continuous, you have to check that. Yeah, it is on the closed interval, because it says that the derivative of the z has to be continuous in the domain. So domain is, closed interval to be. Moreover, the derivative of z is not zero for all t in the interval a to b. So derivative is non-vanishing. In other words, at every point it has the derivative which is not zero. So like its derivative is continuous on the interval and its derivative is not zero on the interval. So we can talk about some of the examples. Let's consider this example. So the previous one, if I take z of t to be cos of t plus iota times sine of t, where t is running between, let's say, 0 and 2 pi, or if I take its derivative, so the derivative turns out to be minus sine t uh, plus iota times cos t. So this is continuous, no problem at all. The condition for one is satisfied, already, because sine and cos are continuous at every point. The next thing that we need to look at is the derivative to be non-vanishing. So let's check where this derivative vanishes. So like we want to see where it is zero. So it is zero at the point where sine t is zero and cos t is also zero. So I need to find out a value t where sine and cos both are simultaneously zero. And in this interval 0 to pi, this is not going to happen. In other words, I don't have any such t where both of these quantities vanish. So I can say that z of t, uh, z prime of t is never zero in the interval 0 to 2 pi, and this allows me to conclude that the z of t, which is basically a circle, is smooth curve, right? So this works as a kind of example for the smooth curve. What is going to be a curve which is not smooth? So we can take some of the examples. Let me show you one example graphic. You can look at this particular curve. This has got a cusp over here somewhere in middle. So that means that at this point derivative does not exist. So like it is, you know z of t does not have derivative at this point. That means when we don't have derivative, then the continuity is, beyond that. So like we can't talk about its continuity. Yeah, so like if a curve is having a cusp, then it is not going to be a smooth curve. But we can take one mathematical example. Let's say if I write z of t to be 1 over t, what should be the example? Like what could be right example? So let's say 1 over t and plus iota times t squared, let's say. And suppose my t is running between -1 and 1. So if I take this way and define this curve, then you kind of find out its derivative, then you will see that there is a problem somewhere. State some of the examples, some of the names. So there is a cuspidal cubic. You can check that its equation is z of t to be t square plus iota times t cube, and this curve is non-smooth, so it is not smooth, right? And you can check asteroid. Its equation is given by z of t to be uh, 2 cos t cube plus iota times 2 sine t cube, and you can also have square root curve defined by z of t to be square root of t plus iota times square root of minus t, and you can have step function curve, absolute value curve. So all of these curves are going to be non-smooth. So this is non-smooth, this is also non-smooth. So these are some of the examples of the curves which are not smooth, right? One more thing is the derivative of the parametric function, or the parametrization, gives us the tangent vector to the curve, tangent vector to the curve 8t. So like this is a curve as shown, and at this point we have found out its derivative, and its derivative is basically a tangent vector to that curve at that point. So if this is a curve, then you find its derivative. So this is a curve and you find its derivative at this point, let's say. So you will see that you will have a tangent vector over here, defined by the derivative of t, right? So terminologies aren't ending, so we are moving ahead to define some more terminologies. So I'll now state what do we mean by a piecewise smooth curve. So I'll talk about a characteristic, in other words, of the piecewise smooth curve. So a piecewise smooth curve C, a piecewise smooth, so a piecewise smooth curve C has continuously turning tangent except possibly at the points where the smooth curves are joined, where the smooth curves are joined. So this is a kind of property of a smooth curve. So smooth curves are going to be C1, C2, Cn. So if I simplify what I've written, is basically, so you take smooth curves. Let's say this is a C1, and you take another C2 which is smooth, and you take another C3 and C4, and let's say you are taking till Cn. So you have got n smooth curves and you join them. So and you move then you see that the behavior of tangent at every point on this piecewise smooth curve. So this curve will be called will be seen as a piecewise smooth curve. So at every point the tangent is going to be having a continuously turning behavior. So at each point the tangent will be turning continuously like this. So that's the characteristic of the piecewise smooth curve. So you can see your piecewise smooth Let me define what do we mean by a contour or path. A piecewise smooth curve C is called a contour or path. So whenever we have a piecewise smooth curve, we will call it a contour. So we have seen that circle is smooth, so it can be called as contour. So if you take a line segment between 2 points, line segment which is smooth, then you can also call it a contour, right? So that's how you can define contour. Now I will define some more notation. Let's now define another notion, which is a simple curve. So we will now define what do we mean by a simple curve in the complex plane. So curve C in the complex plane is said to be simple if what happens if for every t1 not equal to t2, if you are taking t1 and t2 which are not equal, it gives you z of t1 not equal to z of t2. So you can say that if inputs are not equal, then outputs are not equal. If that is happening, that means you are talking about a simple curve. In other words, this except possibly, so there is an exception, except possibly at t equal to a and t equal to b. So the curve can have this property that z of a equal to z of b. This can have, but like other than a and b, if you are taking 2 points which are not equal, then z on those points should not agree with each other as well. So for example, we can give the example of circle. So like if we see we have defined circle to be z of t, which was cos t plus iota sine t. So where t was running between 0 to 2 pi, let's say, right? So now, is there any value where are there any two values t1 not equal to t2 where z1 is not equal to z2? So of course you can solve for this. In other words, we can see that where these two are equal. So we can check where these two are equal basically. So let's see, are there any t1 not t2 where z of t1 is not z of t2? So we can check, are there any? So I will, let's say my z of t is cos t1 plus iota times sine of t1, and let me say that this is equal to cos of t2 plus iota times sine of t2, and then I can write cos t1 minus cos t2 uh, plus iota times sine t1 plus minus sine t2, which is equal to 0. Now I can, from here I can say that cos of t1 is equal to cos of t2 and sine of t1 is equal to sine of t2. So are there any values in the interval 0 to 2 pi where these two agree? So we can check. For example, we can pick, just as an example, t1 equal to pi by 2, and let's say t2 is equal to 3 pi by 2. So you can check that this will hold because cos of pi by 2 is 0 and cos of 3 pi by 2 is also 0. But what will happen over here, on one side you will have 1 and the other side you will have minus 1. So that is not equal. And hence you will have z of t1 not equal to z of t2. In this way you can argue that there are no such t1 and t2 which are not equal, but z of t1 is equal to z of t2. This is not going to happen. So you can say that because for every t1 not equal to t2, z of t1 is other than z of t2, therefore circle is simple. But as I had seen in the as I had stated in the definition, that possibly at the end point 0 and 2 pi, you can check that if you take t to be 0, then this z of 0 is going to be cos of 0 1 iota sine of 0 0. So like you will have 1, and you can check at t equal to 2 pi, which is 2 pi 1 plus 0, which is 1. So like they can coincide at the endpoint, but generally on other t1 not equal to t2, z of t1 is going to be different from z of t2. So this is how you can define your simple curve, right? I can say that in other words that a simple curves do not cross themselves. So if like I should talk uh, counter to this, like if I have a curve which is looking like this, you can see that in uh, this curve is coinciding at this point. So like this is cutting itself, so it's not simple, right? And I can give you some more examples. For example, figure 8 curve. Figure 8 curve. How does it look like? So we can see it. This curve is right over here, and it is basically looking like infinity, right? Which is also called lemniscate of Journo. So it is not simple. Not simple. I can give another example, which is trefoil knot. We can search trefoil knot. Trefoil knot. How does it look like? So this is trefoil knot. This curve is intersecting itself, and this is also not going to be a simple curve. So this is over here. We can also see lemniscate of Bernoulli. Lemniscate of Bernoulli. This is just looking like infinity. It is also not simple curve, and one more curve that I can show you which is not simple is Cassinian oval. So these curves are also not simple. So these are some of the curves which are not simple curves, right? There is another notation which is the closed curve. So we can simply define what do we mean by a closed curve. A curve C uh, parameterized by z of t to be x of t plus iota times y of t for t in the interval a to b is closed if z of a coincides with z of b. So if at the endpoints like a and b the values of z are same, then we can say that the curve is closed. Okay, so you can see circle as an example of the closed curve. So if it is starting over here, like at t equal to a, we have a point over here, then and we move, come back to it t equal to b. So like this is how your closed curve looks like. Ellipse is also a closed curve. uh, Circle is a closed curve, and there can be many more closed curves that you can imagine. But what do we mean by a simple closed curve? Simple curve which is also closed is simple closed curve. In other words, a curve has this property: z of t1 is not equal to z of t2 for every t1 not equal to t2, but so but z of a is same as z of b. For every t1 t2 not equal to t2, where t1 and t2 are running in this open interval a to b. So when you take t to be a and t1 to be a and t2 to be b, so they coincide. So simple closed curve. As we have already seen that circle was simple and it is also closed, the circle is an example of simple closed curve. Circle is simple closed curve. Moreover, it is also contoured, so you can say that the circle is a simple closed contour or path. Now let's define the positive direction or positive orientation of a curve. Orientation of a curve. So how do we define the positive orientation? So we define the positive direction on a contour to be the direction. So it is the direction on the curve that corresponds to the increasing values of the parameter t. The increasing values of t. So t is the parameter that we use in the parameterization z of t, right? And what do we mean by a negative direction? So negative direction or orientation is going to be the one where it is basically opposite to the positive direction. So if you have a curve, then you have to check what is going to be the positive direction for it, and then you have to figure out whether your direction is if it is oriented positively or negatively, right? So in the case of remark, in the case of simple contour, in the case of simple closed curve, the positive direction is along the counterclockwise, where the negative is going to be along the counterclockwise. So counterclockwise is positive and clockwise is negative. Case of non-closed, we say that C has positive orientation if we traverses from initial point to terminal, and we say that it has negative orientation if we traverse it from our terminal point towards the initial point, right?